What is a soil incubation? The term incubation refers to the fact that soils are generally kept at a constant temperature in a controlled environment. Soil incubations in the lab offer a convenient and controlled way to test the effects of variables such as moisture or temperature on soil processes. Changes in the soil are measured over time. In our case, we are curious about soil CO2 efflux, so we will be measuring the amount of CO2 leaving our soils. In order to do this, we will put our soil samples in airtight jars so that the CO2 released by the soil builds up over time and we can measure it. Before we go any further, think about, why do we keep the soil at a constant temperature? Why do we measure CO2 efflux? What does it tell us? Why do we keep the soil in a sealed jar? Why not leave them open? In today's lab, we'll work with Michelle to perform an incubation of our own. We are going to set up a week-long soil incubation and test the effects of moisture and temperature on soil CO2 efflux rates using a factorial design with 2 moisture and 2 temperature treatments. We will have one set of samples at a low moisture content, 25% water-filled pore space, and we'll have another set at a high moisture content, 50% water-filled pore space. These will go in a 15 degrees Celsius incubator, and we will have another full set of samples at 35 degrees Celsius. In this way, we can simultaneously test the effects of moisture and temperature on the rate of soil CO2 efflux. Let's get started. First off, we should know about the instrument we'll be using to measure our samples. We use an instrument called an IRGA, which stands for Infrared Gas Analyzer. An IRGA measures trace gases by determining the absorption of an emitted infrared light source through a certain air sample. This illustration shows the basic idea of an IRGA. An infrared laser is sent through your air sample toward a detector. It is also sent down a sample of reference air, for which you know the CO2 concentration. By comparing the absorption of your sample to that of the reference gas, you can calculate your CO2 concentration. Let's get started with our incubation. To begin, we'll prepare our samples, create a standard curve for our reference gas, flush our samples with CO2-free air, and take a time zero measurement. We will start by weighing out our soils and adding the right amount of water to each one.
So the first thing I do when I start an experiment is I need to weigh out my soil sample. So I've already tared out the cup, and now I'm adding enough soil to get to the weight I want. And usually the range I do, so in this experiment we're doing 32 grams and plus or minus 0.02. So I need to carefully weigh out how much I need, and if I overweigh, take a little bit out.
We are testing the effects of moisture and temperature on soil CO2 efflux, so we need to set up our 2 moisture content treatments. The moistures we have chosen are 25% water-filled pore space, and 50% water-filled pore space.
So the next thing I do after I weigh out my soil is wet it up to the appropriate moisture I want. So in this experiment we're going to do 2 different moistures, and what I'm doing is in advance I had already calculated that I need to add a certain amount of water to get to a particular pore space. So for this sample I'm going to do 50% water-filled pore space. So I have 32 grams of soil, I have the cup, and then to get to 50% water-filled pore space, I'm going to add 4.97 grams of water.
How did Michelle know how much water to add to her sample? She used the following calculations. First, she calculated the proportion of pore space in the soil using the equation proportion pore space equals 1 minus bulk density of the soil over the particle density, which is usually estimated at 2.65 grams per centimeter cubed. Then, she calculated the amount of water to add using this equation. Water to add in grams equals water-filled pore space desired, in our case 0.25 or 0.5, times the proportion pore space divided by the bulk density, all multiplied by the sample mass.
So I will tear out my cup and my soil. Then I will slowly add water until I get to 4.97 grams. And it's important to do this slowly and dropwise. And so I'm adding deionized water, and I'll add it dropwise because I don't want to add too much at once, because sometimes it can pool on the surface of the soil and kind of cause a caked surface. So you do want to do this slowly, and you want to drop it all around the surface of the soil so all of the soil gets equally wet. Once I add the water that I want, then I take the total weight so that in the future, in a long-term experiment, the soil can dry out. That way, if I know what the total weight was, I can weigh the cup in the soil and then make sure that the moisture goes back to that total weight. So this total weight was 49.326. So that includes the soil, the 32 grams of soil, the 4.97 grams of water, and then also the cup. So once we've weighed out our soil and added our water, now we're going to put them in mason jars. So these mason jars have water in the bottom. The reason for that is because soil will dry out, and if we have water in the bottom of the jar, it'll increase the humidity and make it less likely that the soil will dry out. So we'll minimize the soil drying out with the water in the bottom. And then we put our soil in here. And each of the jars is fitted with a little septa. That's where we're going to take our CO2 measurement from. And then we just need to put the lid and the rim on and make sure they're nice and tight. We have to make sure they're airtight for us to measure the CO2 concentration properly.
Now that we have our samples prepared, it's time to measure our standard curve. But what is a standard curve? The purpose of a standard curve is to use some known values and relate them to your unknown values. Multiple samples with known properties are measured and graphed, which then allows the same properties to be determined for unknown samples by interpolation on that graph. The samples with known properties are the standards, and the graph is the standard curve. In our case, we know the amount of CO2 in our reference gas, and we measure the int value, which is the number that shows up on the erga. When we measure our samples, we will measure their int values, but we want to know how much CO2 there is. We get the amount of CO2 in each sample by relating those int values back to our standard curve. Int here refers to integral, because the instrument is integrating under a curve to get each measurement.
So we're going to measure the CO2 concentration in our jars using an infrared gas analyzer. And what I did prior to this is I turned on the air for this instrument, because there's always air that flows through, and I let it warm up for 15 minutes, so that's already done. And now what we're going to do is a standard curve, so that we know if we put a known amount of gas in, what the reading is for that known amount of gas. So we have a tank of known amount of CO2 that I will inject in at different amounts, and that's where we'll make our standard curve, so we know that what our concentration is on our own unknown gas end. So this is our standard tank gas. It's 1,040 ppm of CO2. So what I'm going to do is, before taking my actual sample, I need to flush the syringe with tank air. The reason for that is because on this syringe, this area right here is a dead space that has whatever air was in there on the previous use. So I always flush my syringe with the standard tank air twice to flush out that head space, so that all of the air in this head space is now from the tank. So this is my actual sample I'm going to take. And this is a 10 ml syringe. And for our standard curve, we're going to do 2 mils, 4 mils, 6 mils, 8 mils, and 10 mils. Okay, so I'm going to compress my syringe a little bit. I'm going to do the 2 mil first. I'm going to open up the stopcock, press it down to 2. And then I need to very quickly and firmly press the gas in. And then wait a couple seconds and pull it out. And then we'll do the exact same thing again for the 4 mils, the 6 mils, the 8 mils, and the 10 mils. And you can see right now what it is it's integrating the area underneath the curve. And so this bottom number is our final number. So our value for the 2 mil was 472.66.
Before we take any measurement, we need to flush our jars with CO2-free air. Why? We need to ensure that all of the samples begin with no CO2. This ensures that all of the samples have the same starting point, and it means we know that any CO2 we measure afterwards came from the sample, not from the ambient air that was in the jar when we placed the sample in there. Flushing is done by opening the jars, inserting a tube, and pumping CO2-free air into the jars for about 10 seconds. We then recap the jars and we're ready to measure.
So now that we've weighed out our soil and wet it up and put it in our jar, we're going to do a time zero measurement. So what this is going to be our background number that we will subtract off once we do subsequent measurements later. So the first thing we need to do is we need to mix the jar because we want to make sure that the gas sample we take out is homogeneous and representative of the whole. So we'll use a 60 ml syringe here, and the first thing we need to do is flush the syringe with room air because, like I said before, there's this dead space here and you don't know what concentration that dead space may be from your previous sample, so you want to make sure you mix it with room air. And I'm going to close the stopcock and put it in our jar. What I'm going to do next is draw out a little bit of sample, just a very tiny amount. Close the stopcock. I'm going to waste this sample. And what that's going to do is that's going to flush out the head space here, this dead space here, with the air from the jar. So I'll do that. Now I'm going to mix the sample. So I'm going to go up and down slowly 4 times. Okay, now that we have the sample mixed, we'll take our actual gas sample to put into the infrared gas analyzer. So we're going to use this 10 ml syringe to do our time zero measurement. First thing we need to do is flush the syringe with room air. We'll close the stopcock here, put the syringe in the jar, open the stopcock, and pull out a small amount of sample. And this is just going to flush the head space of our needle. Now we're still going to want to flush with this syringe a couple times before we take the actual sample. So when we take our time zero measurement, we want to make sure that our the sample we inject is within the range of our standard curve. So at time zero, there's fairly low concentration. So I'm going to take a 10 ml sample. I'm going to close the stopcock here, pull it out. I'm going to compress this down to 8. The reason why I compress the sample is because this jar is at atmospheric pressure. Now I've put a syringe in there and increased the volume of the jar. So now the air is likely below atmospheric. So I have to compress it a little bit to get it back to atmospheric pressure. So I'm going to compress it to 9. I'm going to open it up. I'm going to press down to 8. And we're going to inject 8 mils in. I need to do this quickly and in all one shot here. Wait a couple seconds. So it's important for you to record how much sample you injected. So for our first time zero sample, we injected 8 milliliters. And our number for that was 1,178. So we have weighed out our soils, wet them up, sealed them in jars, and taken the time zero measurement. Now we're going to put them in the incubator. So this is our 35-degree incubator. So we're going to have one set of soils that's incubated at 35 degrees. Seal that up. We've got our other set of samples that we're going to put in our 15-degree incubator.
After our samples have incubated for a set amount of time, we will measure the CO2 that is built up in the headspace in each jar. Dividing the amount of CO2 by the time elapsed will give us a rate of CO2 efflux. This rate can be expressed in a number of ways, but one common way is micrograms of carbon per day per gram of soil. This requires converting the mass of CO2 to a mass of carbon and dividing each rate by the mass of soil in each sample. Each time we measure our samples, we need to make a new standard curve. This involves the same procedure that we used before. We need to repeat the standard curve each time we measure because the instrument can drift slightly over time or give slightly different values depending on the day. Making a new standard curve each time we measure ensures comparable values across time. Next, we measure the samples using the same procedure we saw before. We saw the time zero measurement, and a sample measurement is essentially the same. The only difference is that we expect to have more CO2 in the jars than we did before, so we will inject less gas in order to stay within the range of our standard curve. We have also seen how to flush our jars, and we will repeat those same steps, inserting a tube and blowing CO2-free air into the jars for 10 seconds before recapping. It's important to note that there is more than one way to do a soil incubation. Today we have learned about a closed method, where jars are sealed except during flushing. It is also possible to keep jars open for the majority of the experiment, capping them for a short period of time, usually a few hours, prior to measurement to calculate a point flux. What do you think are some of the reasons for choosing to keep jars sealed versus keeping them open to the atmosphere? There are lots of reasons that one might choose one method over the other. For example, if one wanted to study the effects of drying and re-wetting on soil processes, keeping the jars open would allow evaporation and drying over time. In our case, we want to keep soil moisture consistent, so keeping the jars closed helps to prevent evaporation. One important consideration is that as CO2 builds up, it means that oxygen is being consumed. If too much oxygen is consumed, the soils can go anoxic, and that has big effects on microbial processes. It's important to avoid anoxia unless it is an explicit part of the experiment. That's why we flush our samples each time we measure, to flush out the CO2 and add more oxygen. When designing an incubation, considerations like these need to be made to determine the best method to use. Our measurement will yield one CO2 efflux rate value per sample. Now, what do we do with that data? It's time to analyze it. Do we see any significant difference between our treatments? Use the data provided to practice the calculations we saw today and to determine whether the moisture and temperature treatments had significant effects on CO2 efflux rates from our soils. That's all for today's lab. To recap, we learned about the purpose and basic principles of soil incubations. We also understand the procedure and reasoning behind the experimental design of those incubations. And we know how to calculate CO2 efflux from our soils once we measure them on the ERGA.